Similar polygons. The first thing we have to do is understand the vocabulary that's used. And our first one is similar figures. Similar figures are figures that map onto each other using a similarity transformation. Now, we've used those previously this year, and we have to note our angle measurements. The ones that we have used previously this year are an enlargement and a reduction. We did that when we learned dilations. So figures that map onto each other via a similarity transformation. Now, when we learned dilations, we learned about enlargements, and the enlargement happens when the scale factor, or K, is greater than 1. Anytime you multiply numbers by a factor of greater than 1, it's going to get bigger. Or a reduction. Now, the reduction, in order to get smaller, many people think you multiply by a negative, but that's actually not the case. You want to multiply by a number that is between 0 and 1. So any number that is between 0 and 1 will make a shape get smaller. And remember that these are dilations. Now, scale factor is the amount each side length is multiplied by. So the amount each side length is multiplied by. We write scale factor as K. That's just something that we do. Now, corresponding parts of similar polygons. When we look at these shapes, we look at what things line up together. Now, in our picture that we have here, we have shape number 1 and we have shape number 2. And we're looking at the things that correspond with each other. So let's list those. We have side AB. It corresponds with side WX. We then have BC, which corresponds with XY. DC corresponds with ZY. And finally, AD corresponds with WZ. Now, this is exactly the same as when we did similar triangles, and we've talked about when triangles were congruent and we wrote congruency statements, but now all we're doing is labeling the sides that match up. We also need to make sure we pay attention to the angles. So we have angle A and angle W, angle B and angle X, angle C and angle Y, and angle D and angle Z. Now, if we look and we see or told that this angle is 90 degrees and this angle is 90 degrees and this angle is 70 degrees, that's going to make this 110. Now, some people say, how do you know that those 4 angles together add up to that amount? Well, I'm going to show you. There is a nifty little formula, and I'm going to put it way up here at the top. And the formula is the number of sides minus 2 multiplied by 180 degrees. So if I take the number of sides, which in the case of my example here is 4 minus 2 multiplied by 180, 4 minus 2 is 2 times 180. That's going to give us a total of 360 degrees. So every single four-sided shape has interior angles that equal 360 degrees. Now, because my smaller shape has angle measurements of 90, 90, 70, and 110, we look at number 2, and that one will also have 90, 90, 70, and 110. The angle measurements in similar shapes will be exactly the same, no matter the difference in size. Now, if we look at our similarity transformation, we're doing an enlargement. That means that whatever we do to the left side, we do it to all of the sides, and it's going to become the right side. So if the measurement were 1.5 and I had a scale factor of k, but we use it as a 2, so k equals 2, 1.5 times 2 is 3. You simply multiply all of the sides by the scale factor. Now, next we'll talk about our statement of proportionality. In our statement of proportionality, we have to label the things that match up, just like we did right here. However, we are usually told in a problem whether to put the smaller one or the big one on top. Typically, if you're not told otherwise, you put the second shape on top. So in this case, the bigger one is on the right. So we put big on top, small on bottom. Now we make our statement of proportionality. So we have WX is proportional to AB, which is the same as XY, which is proportional to BC, which is the same as ZY, which is proportional to DC, the same as WZ, which is proportional to AD. Now that covers our four sides. All of those will simplify down to the scale factor. So our similarity statement in this one would be that ABCD, which is our shape, is similar to WXYZ. In this problem, we look at diagram ABC is similar to WXY. So that means that A corresponds with W, B with X, and C with Y. Now, we're asked to find the scale factor from triangle ABC to triangle WXY, and we're asked to list all pairs of congruent angles and write the ratios of the corresponding lengths in a statement of proportionality. So the very first thing we want to do is start at the bottom. So we have ABC and WXY. If you look at the similarity statement up here, you will notice that AB is listed first and WX is listed first. Those two correspond. So we will go ahead and say that WX corresponds to AB because we're using our second shape first. That should be the same as the second set of letters, which are XY, which is proportional to BC. And then finally, our third one, which is AC and WY. So WY and AC. And these together will give us our scale factor. Now, let's go ahead and put the numbers together of which lengths match up with these. So we're going to say WX is 5.4, AB is 3. Then we have XY, which is 7.2, and BC, which is 4. Then we have WY, 4.5, and AC, which is 2.5. If you're ever asked to find out if two shapes are proportional, you're going to set them up just like this, and when you simplify the fractions, you're going to find that they all will simplify down to the scale factor. So let's look at these. 5.4 divided by 3 is going to simplify to 1.8. Then we take and we put 7.2 divided by 4 into the calculator. It's also going to simplify to 1.8. Now, there may be times that you have two of them simplify to the scale factor and the third one doesn't, but don't let that fool you. You always want to simplify all of the fractions. Now, the next one is 4.5 divided by 2.5. And if you put that into your calculator, it simplifies to 1.8. So that's going to tell us that our scale factor is going to be 1.8. So you would take everything in the first shape, all the sides, and you would multiply it by 1.8 to get the second one.